Good afternoon. This is our 719 Mathematical Economics. Today, we're going to start studying dynamic optimization and discrete time models. So let me share my screen now. Okay, so let's minimize this. So now you must be able to see my screen, my whiteboard. So again, so this is dynamic optimization in discrete time. Okay. And when we say time, we basically mean that we are working in a subset of integers. Okay. Now we're going to see two approaches. One is called the sequence approach. Okay, and the other is called dynamic programming. Now, this is also called recursive approach. Okay, so we're going to see both approaches and mostly focus on dynamic programming because it is much more intuitive and simple. Okay. So the typical problem will be like this. So there will be a state vector. Okay, so that will be an element in some, let's say, subset of Rn. So this is the state vector. Okay, and there will be a control vector. Okay, so the state vector will be your state variables, S1t, S2t, dot, 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 Snt, okay? And Ct is your control vector, so these are your choice variables, okay? And the problem will be like something like this. So in the most simple case, I mean, in the simplest case, you will have something like this. Let's write a finite version. Okay, so you will have some reward function here. Okay, that reward function will be a function of your state vector and your control vector. Okay, then there will be a discounting term where beta will be between 0 and 1. Okay, and also, of course, you're going to have some relationship that describes the evolution of the state vector. Now, usually, in the most general case, we use a set to describe what is feasible given your choices of given your choice of Ct and given your state St. Okay. So this will be a set in general, but more specifically, we're going to write transition equations. And obviously, in the beginning, you will have the initial state known, right? So that's the most general specification of the problem. Actually, not the most general. I'm sorry. For this to be most general, we would add time into these functions and time into this set. Okay. Now that would be rather general. So here we also have two cases. T could be finite or T could be infinite. All right. Now, these are the types of problems that we are going to attack. All right. Now, I will first explain the sequence approach for finite T, okay, using a simple optimal growth problem. it is always easier to understand the material using this simple optimal growth problem, because you already know the solution to this in continuous time, right? Remember the Ramsey model, right? So in continuous time, you know how this works, right? So now in discrete time, we're gonna see a particularly simple version of it, and we use a sequence approach first to attack the problem. Okay. So in the optimal growth problem, we have this, right? So we maximize starting at t. Of course, I assume that time starts at 1 and now goes to some finite t. All right. I have the discount factor. So this is the discounting term, beta t. Then I have this period utility function. See, here is my consumption. Okay. Now this problem is subject to what? First, there will be some non-negativity constraints. And now you understand that KT is the capital stock. And the sum of my saving and my consumption will be less than or equal to my output. Okay? And finally, I'm going to assume that initially we know K, K0. Okay? So obviously here, C is your consumption and K is capital, right? Now KT, that's important. So KT is the capital stock at the beginning of period T, right? So so if you imagine time passing through discrete episodes, right? So this is T equals 0, let's say. This is T equal 1. This is T equal 2, then that goes on. So here at that point, you have K0, then you will have the output, then you will choose C0, then this will determine your K1. Okay? Then you're going to have output, then you're going to have consumption, and that will go on. Okay? K2. So timing is important. So be careful with the time indexes. All right. Now, obviously, how do you proceed? Well, this is a finite dimensional problem. So you have a function here. So this is a weighted sum of utilities. These are the U function here is called period utility function. Okay, and this whole thing which you can denote by ut, the big U, that would be intertemporal utility function. Of course, it is a function of C1t. Sorry, it's a function of C0, C1, dot, 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 right? CT. So this is called intertemporal utility function. Okay. And F is the production function, obviously, right? So F is a production function. And here we assume, as you see it, we assume that there's full depreciation, right? So there's output. For you to have capital stock next period, you're gonna save it. The existing capital stock fully depreciates from one period to the next. Okay, that's just for simplification. Some of the methods, of course, will not work. The analytical solution will not be found when there's depreciation, but in general, this simple version is good for understanding the mechanics. Right? So how do you solve this problem? Of course, we here require that U and F are well behaved. What does it mean? Well, U and F are well behaved. Let's say U is increasing, the second derivative is less than 0, so it is strictly concave. So F is increasing, the second derivative is less than 0, F is strictly concave. You can also assume in other conditions, what we call in other conditions. Okay, so if C goes to 0, then marginal utility goes to positive infinity. If C goes to positive infinity, marginal utility goes 0. Similarly, for production function, if K goes to 0, marginal productivity goes to positive infinity. If K goes to positive infinity, marginal productivity goes to 0. Finally, here you can assume that capital is an essential input. So if you have no capital, you have no production. Okay, so these are pretty restrictive, as you see. It is too much, actually. So sometimes we don't need that. For instance, we may have F to be just quasi-concave, U to be concave for the existence, but strict concavity guarantees uniqueness as well, etc. So you know that part very well from our earlier study of nonlinear programming problems and the Hamiltonians, in the continuous time. But for simplicity now, I'm assuming all these together. All right. So the problem is really well behaved, and you also realize that this feasible set is now compact and closed, right? So it's closed and bounded. So I have CT plus, CT plus KT plus 1 less than or equal to FKT, and I have CT greater than 0, KT plus 1 greater than 0 or equal to 0. Right? So this set. So what is the set? The set is on one side it is 0, right? On the other side it has FKT CT. So if you actually set CT to 0, so this is your upper boundary and this is your lower boundary, right? So the set is closed and bounded. So you may always, of course, express the problem by eliminating C. And by the way, we are assuming, of course, that U and F are continuous. I mean, it's pretty obvious, but we assume that they are continuous functions, okay? So the only thing for now that you can do, so in the sequence approach, you're gonna do this approach, right? So what you're gonna do in the sequence approach is to write the Lagrange, okay? So your Lagrange is now this, right? So beta t UCT plus. Now you have constraints for each period, right? Then for each period you must have some Lagrange multipliers. Okay, so that's it. Now you want to write the first order necessary conditions, obviously, right? First order necessary conditions. Now I'm going to do that in this way. So for CT, remember that, I mean, notice that this is all additively separable, right? So if you write this explicitly, right? So if you want to write utility explicitly, you have something like this, right? And that goes on. So it is all additively separable. So I can take derivatives, right? So for CT, I have something like this. So first I have beta t, right? Then U prime CT. Then where do I find CT again? Here, right? So it is minus lambda t, right? Now this must be, of course, since I have non-negativity constraint, this must be like this. beta t u prime ct minus lambda t equals 0 and ct equals 0. Now, this must be true for all t, okay? From 0 to t, okay? Because I'm taking this derivative for all of my control variables, right? For all of my control variables, I'm taking this derivative. So starting from C0, C1, C2, dot, 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 until I find the last episode here as CT, okay? So that's good. Then, of course, I will have the constraints, right? So let me write the constraint part in this way. So so you have fkt minus ct minus kt plus 1, right? So this will be greater or equal to 0. And then you have lambda t fkt ct minus kt plus 1 equals 0. And you have lambda t greater or equal to 0. Now I want to write this for these episodes, okay? So the last episode, the last period, I'm gonna deal with this later, all right? For now, let's try to understand that, okay? So let me just check one thing. Yes. So now there's also your kt plus 1, right? Now, kt plus 1 is kind of your control variable, right? Because once you choose consumption, of course, it is related with the constraint as well, but you also somehow choosing kt plus 1. So you must have some optimality condition there as well. You must have a cost state equation, basically, right? You must have some way. You must be smart enough to optimally accumulate capital from one period to the next, because as you see here, your consumption decision today affects your feasibility set tomorrow. Okay, so how to choose KTs? Sorry, KT plus 1s, right? Because K0 is already given. So you want to take first the derivative with respect to K1, right? So your choice variables now for in this one, you have K1, K2, dot, 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 KT, and finally, when T is equal to T, you're gonna have KT plus 1, right? So the first choice here is K1. So where do you see K1 here? So the derivative with respect to K1 is like this. Minus lambda T, right? Because here, when T is equal to 0, you have K1 here, right? So its derivative is minus lambda T. Then, in the next one, you have lambda T plus 1, FKT plus 1 here, right? So you have lambda 2. Oops. So when T is equal to 0, you have lambda 0. So you have minus lambda 0 here. When T is equal to 1, you have lambda 1. So it's a plus. Then you have the derivative. Okay. Now this derivative, of course, must be less than or equal to 0. Then your KT plus 1 times this derivative equal to 0. Then your KT plus 1 must be greater than or equal to 0. But now, once again, I am doing that for for this period, and then I'm gonna deal with t equals t later on. Okay, so I have to now take the derivative with respect to kt plus 1. Okay, kt plus 1. So when t is equal to t, all right, I want to take the derivative with respect to kt plus 1. Okay, so what is that derivative? Well, that derivative is basically minus lambda t, right? So this must be less than or equal to 0, right? Because it is here. When t is equal to t, the last constraint, I have lambda t here, this one, and that's derivative with respect to kt plus 1. Okay? Then I must have lambda t times this one must be equal to 0, right? And I must have kt plus 1 less than or equal to 0. Now this is for t equals t. Okay? And finally, let me reserve some space here. And finally, I must have the constraint for the last episode. All right. So the constraint for the constraint for the last episode. So it looks like that. So I have fkt, all right, minus ct minus kt plus 1 greater than or equal to 0, lambda t, right, fkt minus ct minus kt plus 1 equals 0, and lambda t greater than or equal to 0. Okay, now I have for each and every episode, so this is again for t equals t. Okay, now I have every single first order condition for the entire episodes, right? Because the first equation here is true for all t. All right, so these are my control variables, these are my choice variables. Now kt plus 1 is also a kind of a choice variable. Okay, so that must be true, but I'm paying particular attention to the last period. Why? Because there will be no tomorrow, right? So I have to be careful with this. So I wrote this. So compare this and this. Compare these two first order conditions. Here, obviously, since there is no lambda t plus 1, this part is 0, right? For the last period. Then this must be true. All right? And we have that. Now, do you have any questions? As you see, the sequence approach is a bit messy, but we're gonna learn something very useful out of it. Any questions? So far, what we are doing is just nonlinear programming. Okay, this is just nonlinear programming you learned in the first week of this semester. There is an objective function. There are constraints. Some of them are non-negativity constraints, and some of them are inequality constraints. So we write these constraints and objective function within a Lagrange, and we take the first order conditions. Okay, that's all. That's all it. But here I should be careful with the last period, because at the last period the world ends. Okay, so I must be careful with lambda t there. All right, that's all I'm doing. Nothing really complicated. Okay, if you look at this carefully, this is just a very simple problem, but this is messy. It's a bit tedious. Okay. Now, how to proceed? I want to find, of course. So be careful what we are choosing. So we are choosing C0, C1, CT. In the meantime, we are choosing K1, K2, KT, KT plus 1. Okay? And we are doing so by finding this particular path of lambda. Okay? So that lambda will be your, of course, kind of your cost state variable. Okay? So this is how we proceed. Well, we assume that U is strictly increasing, right? So this plainly tells you that, you know, budget constraint will always, I mean, okay, so this is positive. So look at the assumptions. This is positive, and this one goes to positive infinity, right? So these two imply that CT is strictly greater than 0 for all t. Okay? Then you also have, from the first equation, remember the first equation is like this, U prime CT lambda t. So this, of course, tells you that lambda t is, of course, always positive. Lambda t, of course, always positive means your constraint, okay, holds with strict equality. Okay, so now I have, I mean, when I write this stuff, it will be much simpler. First of all, I have this from the first equation. Okay, I have this from the first equation. Then I have the constraint. So the constraint will be like this, fk. So this is true for all t, be careful. So fkt will be equal to ct plus kt plus 1. So this is true for all t again, because lambda t is positive for all t. All right. Now I have this equation for the last period, and I know these as well. Okay. Now at this point, you realize that since this is positive, this must be 0, right? Right? Otherwise, it would not be optimal to leave some capital. Oh, we have less than a minute. So let's meet at 1:55, okay? Is that good for everybody?
Okay, yes.
All right, let's meet at 1:55, all right? We're gonna continue exactly where we are.